All right, our first example problem is a line integral that has a component with respect to x and a component with respect to y. Okay, so doing this the method that we had originally learned for line integrals with respect to x or with respect to y, this would turn into the line integral over c of, so what do we have here? We have negative, and this would be x of t squared y of t. And then the dx would turn into x prime of t dt. And then I'd have plus x of t y of t squared y prime of t dt. So to do that, we need a parameterization for our unit circle. So we'll just use the obvious parameterization here. So here is the unit circle. And this is our C. Okay, that's the with positive orientation. And of course, it's a unit circle, so the radius is 1. And I'm going to have for my parameterization, x is cosine t, y is sine t, and t goes from 0 to 2 pi. Okay, so let's go and plug into the equation we've written here. So this is going to be the integral from 0 to 2 pi. And let's see, what are we going to have here? We're going to have a negative cosine squared t, sine t, and then this is going to be a negative sine t, plus cosine t, sine squared t, and then y prime is cosine t dt, which is going to become the integral from 0 to 2 pi of, let's see, I have two negatives here, so this is going to be cosine squared sine squared. And then I'm going to have another plus cosine squared t sine squared t dt, or 2 cosine squared t sine squared t dt. Okay, so what are we going to do here? I think the easiest thing to do would be to use the, let's see, what am I going to use? I'm going to use the sine double argument property. So notice I can rewrite this as, okay, this is 2 times, sorry, let me back that up a second. I'm going to rewrite this as half times 2, I'm just multiplying in a 1, and then cosine t sine t squared. There's several ways you could do this. So we could use the half argument properties as well, but this was just the first thing that popped into my mind. So then here I'm going to use the sine double argument property. So I'm going to get the sine of 2t right there. Okay, and then I'm going to get a 1/4 from squaring the first term. Okay, so now I have 2 times a fourth, the integral from 0 to 2 pi of, well, it's sine 2t squared. And now I do have to use the half argument property. Sine squared a is, so this is, what do I have now? I have a half. And then sine squared is 1/2, 1 minus cosine of 4t dt. Okay, so what do I have now? I have a fourth, and I can integrate now. This is going to be t minus 1/4 sine 4t from 0 to 2 pi, which is 1/4, and I'm going to plug in, and I'm going to get 2 pi minus 0 plus 0. And so I get pi over 2. Okay. Now, that certainly wasn't difficult at all. However, Green's theorem gives me another method for how to evaluate this. Okay, so let's look at the same problem again. And this time, let's do it using Green's theorem. So I'm going to write out the theorem just so we can look at it while we're figuring out how to do this. So it's the line integral over C of P dx plus Q dy equals the double integral over the bounded region D of partial Q partial X minus partial P partial Y dA. Okay, so a couple of things. We still have, okay, well, let's write out what's going on here. All right, so P dx and Q dy. P dx and Q dy. So our P is negative x squared y. And so dp dy, the partial derivative of p with respect to y is negative x squared. And then our q is xy squared. So partial q partial x is y squared. Okay, so plugging that in, we are going to get that our line integral over C of negative x squared y dx plus xy squared dy equals the double integral over D of partial q partial x minus partial p partial y. So that's going to be a minus negative x squared, which is going to become a plus x squared. Well, you see now that this is going to be a much simpler integration. Our region is a circle, so now it's going to be very straightforward to turn this into a polar integral. Okay, so here's C with positive orientation. And here, of course, is D. So D is the unit disk. Okay. All right. So now I can rewrite my integral as I can rewrite my integral as the integral from 0 to 2 pi, the integral from 0 to 1, and of course x squared plus y squared is r squared in polar, and then I need my magnification factor, which is r, and dr d theta. So this is going to, r cubed is going to integrate to 1/4 r to the 4th. And so I'm going to get 1/4, and then I'm going to get theta from 0 to 2 pi. And I get pi over 2. So you can see In this example that I've done two ways, it's actually pretty reasonable to evaluate the integral using either method, but often one method is much easier. And often Green's theorem can take a very difficult or impossible integral and turn it into a very easy integral. All right, let's move on to our next examples. So the next example, I'm actually giving you a formula here. If if C is a simple closed curve and D is the simply connected region it bounds, then the area of D is, the positively oriented line integral over C of x dy, or the positive oriented line integral over C of negative y dx, or the positively oriented line integral over C of 1/2 x dy minus y dx. Okay, so you can see I've given three area formulas here. And this third one, you probably can recognize, this is actually the average of 1 and 2. Okay. All right, so let's prove this. Okay, so proof. We can use Green's theorem to prove this. So I'm going to do 1 first. Well, the line integral over C of x dy, if you think of that as a sum of a line integral with respect to x and a line integral with respect to y, so I'm going to write this as 0 dx plus x dy. Okay, so again, Green's theorem, let me just write it up here one more time so we remember what it looks like. Green's theorem says the positively oriented line integral over C of p dx plus q dy equals the double integral over d of partial q partial x minus partial p partial y dA. Okay, so now you can see in this problem that I'm doing here, p is 0 and q is x. Well, that means that partial q partial x is 1 and partial p partial y is 0. Okay, so now I can rewrite this integral using Green's theorem as the double integral over d of 1 minus 0 dA. Well, that is, we know from previous lessons that the double integral of 1 over a region gives the area of that region. Okay, so let's do one more here. So I'm going to go ahead and do 2. I'll prove 2 using the same an analogous method. Okay, so I have the line integral over C of negative y dx. Well, that's the line integral over C, positively oriented, of negative y dx plus 0 dy. Okay, so again, I have P is negative y, Q is 0. So that gives me partial Q partial x is 0, partial P partial y is negative 1. So now using Green's theorem, I'm going to get that this equals the double integral over d of 0 minus negative 1 dA, or the double integral over d of 1 dA, which is the area of region D. Okay, so I've now proved the first two of these, and we're going to use the third version. I'll use that in our next example. Okay, so example 3, find the area of the unit circle using the formula for area given in the previous example. Since I proved 1 and 2, I'm going to use form 3 of the formula for this problem, okay? So, of course, the parameterization for, well, first let me write that formula back on here so we can remember what it was. Area of D equals the positively oriented line integral over C of 1/2 x dy minus y dx. Okay, and I'm just going to integrate with respect to y and with respect to x using the formulas that we know. So I need a parameterization for the unit circle. So I'm going to say x, let's let x equal cosine t and y equal sine t, and t is going to go from 0 to 2 pi. Okay, so there's my parameterization. I'm just going to go ahead and plug on in here. Okay, so we have the area of the unit circle is going to equal, plugging in here, the integral from 0 to 2 pi of 1/2. All right, I need x of t, which is cosine t. Then I need y prime of t, which is also cosine t, dt. And then minus y of t, which is sine t, and dx dt, which is negative sine t, dt. And you can see this is going to turn into a nice easy integral because I'm going to get cosine squared t plus sine squared t, which is of course 1. Okay, and so that is just going to integrate to t. So nice and simple, I get it's actually going to integrate to 1/2 t. So this is 1/2 t from 0 to 2 pi, which is 1/2 2 pi minus 0, or just pi. And of course, we already know that because you know that the formula for the area of a circle is pi r squared. And our radius for the unit circle is 1. And so I should get pi. Okay, next example. Calculate the line integral over C of x to the 4th dx plus xy dy if C is a triangle from 0, 0 to 1, 0 to 0, 1 to 0, 0. Okay, let's draw a picture of C. And you'll see why this is a great candidate for using Green's theorem. Okay, so I'm going from 0, 0 to 1, 0 to 0, 1, and then back to 0, 0. So this is positively oriented. If I walk along that curve, the region here, which I'm going to call D, will be to my left. Okay. If we do this directly without using Green's theorem, then we would need to use 3 separate integrals. It would be a lot of tedious work because we would have to break this up into a C1, a C2, and a C3 and evaluate 3 separate line integrals, parameterize. It would be really tedious. But C is a simple closed curve with positive orientation bounding this simply connected region D. So great candidate for Green's theorem. Okay, so this is up here, this is going to be P dx, and this is Q dy. Okay, and so let's set up how we're going to do our integrals. P is x to the 4th. That means partial P partial y is 0. Well, that's going to be nice. Q is xy, so partial q partial x is y. All right, so a couple of other things I just need to, so we have our line integral over C, positive orientation, of x to the 4th dx plus xy dy is going to equal the double integral over D of y minus 0 dA. Okay, so this is going to be super simple to integrate. I just need to think about my boundaries for D. So I have over here, this is y is 0. And then over here we have x is 0. And then here on the third side, I have y equals 1 minus x for this boundary. Okay, so what are my limits of integration going to be? I'm going to do dy dx, I guess. So x goes from 0 to 1, y goes from 0 to 1 minus x. And I'm integrating just y. Okay, so that's going to be 1/2 y squared from 0 to 1 minus x. And that's just going to give me 1 minus x squared. Okay, so remember, if you are doing a u sub, if this were your u, 1 minus x, you'd need a negative sign for your du. Okay, so this is going to be 1/2. I need a negative 1 for the du, and then I'm going to get a 1/3 1 minus x cubed from 0 to 1. So that is negative 1/6, 0 minus 1, which is 1/6. So great example of how Green's theorem can turn what could be really, really tedious work into something much more simple. All right, example number 5. We have the positively oriented line integral over positively oriented C of 3y minus e to the sine x dx plus 7x plus root y to the 4th plus 1 dy. Another one where, yes, this looks pretty hideous and annoying. Can we use Green's theorem to simplify things? And we can, otherwise I wouldn't be doing this example. Okay, so what do we have here? Let's get a picture of our curve C with positive orientation and our region D. Okay, and this is a circle with a radius of 3. Okay, so I'm going to, okay, now let's go back here. So this section here is my P. Oh, come on. Okay, that's going to be P. And then this section here is Q. Okay. All right, so I have P is 3y minus e to the sine x. And just looking at this, you can see you're going to get rid of this whole e to the sine x when you find partial p, partial y. Partial p, partial y is 3. So you can already see how this is going to become so much more simple. And then here, q is 7x plus root y to the 4th plus 1. Partial q, partial x is 7. So I have a line integral over a positively oriented curve C bounding a simply connected region D, which is going to allow me to apply Green's theorem. So this is now going to be the double integral over D of 7 minus 3 dA. And great candidate for polar here. So this is going to be 4 times the integral from 0 to 2 pi, the integral from 0 to 3, and my magnification factor is r dr d theta. Okay, so I have 4, and then I'm going to get a theta from 0 to 2 pi, and I'm going to get a 1/2 r squared from 0 to 3, which gives me, what is this, 4 times 2 pi times 1/2, oops, and then I'm going to get a 9 minus 0. So what is that? The 2 and the 1/2 are going to cancel, and I wind up with 36 pi. All right. Okay, last example. Find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. Okay, so we're going to use one of the area formulas that I gave in example 2. I'll just use the average one. Doesn't really matter which one you use. They're all going to come out great. Okay, so let's parameterize our curve. So this is x over a squared plus y over b squared. Well, we know that we're going to parameterize and make that cosine squared, oops, let me fix that, cosine squared t plus sine squared t equals 1. So that tells me that I'm going to let x over a equal cosine t, and or x equal a cosine t, and y over b equals sine t, or y equal b sine t. Okay, so why don't we use the average? The area bounded by curve, this ellipse, curve C, which why don't I draw a picture of it? Okay, so we are going to have an ellipse that looks like this. Okay. And we're trying to find this bounded area here. Let's go back. We're going to label this C, label this bounded area D. And, of course, our interval for our parameterization would be t is going from 0 to 2 pi. Okay. So the area formula that we had earlier, the area of D is the line integral over positively oriented C of 1/2 x dy minus y dx, which is the average of the first two. Okay, so this is going to be 1/2 the integral from 0 to 2 pi. Oh, I'm going to run out of room here, so let me move this down a little bit. Okay, 1/2 the integral from 0 to 2 pi x, which is a cosine t, dy dt, y prime, is b cosine t, minus y, which is b sine t, x prime, which is negative a sine t dt. And you can already see this is going to turn out really nicely because I have 1/2 the integral from 0 to 2 pi of ab cosine squared t plus ab sine squared t dt. And of course, you can see how we can simplify that. So this is ab cosine squared t plus sine squared t, which is ab times 1. Okay, and of course, in this problem, a and b are constants. So that is just going to integrate to abt. 1/2 ab times t from 0 to 2 pi, which is 1/2 ab times 2 pi, which integrates to ab pi, or I'll write it as pi ab, which hopefully you remember is the formula for the area of an ellipse. If you think about it, it's a lot like the formula for the area of a circle, pi r squared, but instead of using radius squared, it's using the length of half the length of the minor axis and half the length of the major axis of the ellipse, A and B.